In the previous lecture, we finished by talking about renewal processes. Those are sequences of random variables that are non-decreasing, where the interarrival times, xn minus xn minus 1, as n progresses, are IID random variables that are non-negative, since it's a non-decreasing process. Now, whatever distribution we'd like to set down for those interarrival times determines the properties of the process, and in particular its counting process, which counts the number of steps that are taken by time t. The most basic renewal process is one where those interarrival times have a memoryless property. And let's talk a little bit about that property right now. Suppose you're standing at the bus stop waiting for your bus to arrive. You know that you've been waiting already for 7 minutes. Does that affect how long it's going to take for the next bus to arrive? Well, it depends. If you know that the buses are on a schedule and come every 10 minutes, then each minute that you wait definitely brings you 1 minute closer to when the next bus will come, if they're running on time. But what if the arrival times are not predetermined? Now that would make for bad city planning, but we can think of examples where that is more realistic. Probably the best example is in chemistry and physics, where the interarrival times we're talking about are collisions of particles. If we have a gas in this room, and we know that the molecules of the gas are moving around randomly and crashing into each other, when two molecules collide and recoil off of each other, we can think of a clock starting for when the left particle will hit the next one after it bounces off. Now, does it matter how long it's been since its last collision for how long we have to wait for the next one? No, because everything is moving around in a random soup. So in such situations, we would expect our interarrival times to have a memoryless property. That is, given that I've already been waiting t seconds, the probability that I have to wait s more seconds should be no different than the probability that I have to wait s seconds right from the moment that I got there. It turns out that there's only one parameter family of non-negative distributions that have this memoryless property, and that is the exponential distributions. Recall that a random variable is said to be exponentially distributed with rate lambda if its complement CDF, that is the probability that the variable is greater than or equal to t, is equal to e to the minus lambda t, or just 1 if t is less than 0, since these are non-negative random variables. Now we can just explicitly compute that property that I was talking about. What is the probability that this wait time c is bigger than or equal to t plus s, given that it's already bigger than or equal to s? I've already been waiting s seconds. What's the probability I have to wait at least t more seconds? Well, let's just write this out from the definition of conditional probability. That's the probability that c is greater than or equal to t plus s and c is greater than or equal to s divided by the probability that c is greater than or equal to s. Well, here's the thing. If c is greater than or equal to t plus s, then it's certainly greater than or equal to s. And so we can just erase this superfluous second condition. And that, by what we have written here, because we're assuming t and s are greater than or equal to 0, is equal to e to the minus lambda t plus s divided by e to the minus lambda s, which is just e to the minus lambda t. And that is the probability that c is greater than or equal to t. The probability that you have to wait at least t more seconds after you've already been waiting s seconds is the same as the probability you have to wait t seconds from the moment that you got there, no matter how long you've been waiting already. It is for this memoryless property reasons that exponential distributions are typically used to model wait times in these kind of rare event situations. Now, to be clear, exponential distributions are used because they're the only ones that have this memoryless property, and we can see that as follows. Let's let little f at t denote the complement CDF of a random variable which is assumed to have this memoryless property, but we don't yet know that it is an exponential random variable. So here, f is a function from the non-negative reals into the unit interval. We know that it is a non-decreasing function because it's a complement CDF. And now here's a bit of measure theory that's beyond what we studied in this class. It follows, since it's non-decreasing, that it is actually differentiable, Lebesgue, almost everywhere. That follows from the Lebesgue differentiation theorem, which you can look up in a standard measure theory textbook beyond what we studied in this course. Now, differentiable almost everywhere doesn't mean we can just differentiate it and be happy, but we'll see from the memoryless property that it will actually mean that it is differentiable everywhere, because we can rearrange from the definition of conditional probability the memoryless property to say this: the probability that C is greater than or equal to t plus s is the product, the probability that C is greater than t, times the probability that C is greater than or equal to s. Which means that this function f has the property that f at t plus s is equal to f at t times f at s. Now we know that property is shared by exponentials, and we'll see in a moment that it's only shared by exponentials. Because we can now try to compute the derivative of this function. Let's take f at t plus h minus f at t divided by h. Well, before we take a limit, we note that that is equal to f at t times f at h minus f at t divided by h, which is just f at t times f at h minus 1 over h. And now we're in a bit of a pickle, because the derivative of this is the limit as h goes to 0 of that. But we see that that limit either exists or does not exist for all t, because it's just a question of whether the derivative at 0 exists. If this limit exists, then this limit will exist, and we satisfy a certain differential equation. If this limit doesn't exist, if f is not differentiable at 0, then f is not differentiable anywhere. However, we know that this function is differentiable almost everywhere. So since it's differentiable at least one point, it follows that it must be differentiable everywhere, and in particular at 0. So therefore, that derivative at 0 must exist. It must be a non-positive number since f is a decreasing function. So let's just call it minus lambda for some non-negative number lambda. But that means from this calculation here, taking the limit, that f prime at t for ht is equal to minus lambda f at t. And we know the solution for that is f at t is equal to f at 0 e to the minus lambda t. Now, since we assumed that our random variable is positive valued, that means that f at 0 must be 1. And so we have established that these are the only distributions that have this memoryless property, which is why we're going to use them to model wait times. So let's take an IID sequence of exponential random variables with rate lambda and consider the associated renewal process, which is just the sum of n independent copies of that exponential random variable. We will be interested primarily in the counting process associated to that renewal process, which is nt here. And again, that just counts the number of xn's that are in the interval 0 up to t. We can write that alternatively, as I said, since this is an increasing sequence, as the largest n for which xn is less than or equal to t. But we'll see why writing it in this form is going to be useful for some computations later. Now, one critical thing that we're going to use over and over is identifying the following. This counting process takes values in the non-negative integers. And the event that nt is equal to a particular non-negative integer little n is exactly equal to the event that xn is still less than or equal to t, but xn plus 1 is greater than t, just right away from here. Now, this particular renewal process, where the inter-arrival times are exponentials, is called the standard Poisson process of rate lambda. We would like to now understand this process fully, and for the time being, what I'll mean by that is that we would like to understand its finite-dimensional distributions. We want to be able to take the random variables nt1, nt2, up to ntk for any sequence of positive times and describe the joint distribution of those random variables. Well, to move in that direction, I want to make an important observation first, which holds for any arrival process. The xn's in the process are non-decreasing. So that's just to say this. And in our case here, where the inter-arrival times are almost surely strictly positive, that means that with probability 1 for each fixed n, we get a strictly increasing sequence of arrivals. So that means if I want to describe the distribution of the random vector x1 through xn, it can't be just anywhere in Rn. It can only be in a certain sector of Rn, which is described here. Delta n is going to be the set of sequences of n real numbers that are strictly increasing. That's where these random variables live. And we'll also look at a truncated version of that, delta n of t, which is the set of vectors in Rn whose sequences are strictly increasing and all less than t. Now the first thing I'd like to note, which will be important to us, is that the Lebesgue measure of this set, delta n of t, can be computed explicitly. Its volume is t to the n over n factorial. Now there are a couple of ways that we could see that that's true. It's actually pretty easy to prove by induction using integration, but I'd like to do it in a slightly more invariant way that will set us up for how we're going to use it. And that is to note that you can basically tile all of space with n factorial congruent copies of this set delta n of t. That is, if I fix any permutation sigma in Sn, I can interpret sigma as an orthogonal transformation of Rn. That is, u sigma is the function of n variables, which takes x1 through xn to x sigma 1 through x sigma n, just permuting the indices. Now, doing that, what I see is that the whole cube, 0t copied n times, is basically the disjoint union over all permutations of the image of those orthogonal transformations of delta n of t. That is, I'm saying, well, instead of having just the entries being strictly increasing, I consider the ones where we have x1 is the smallest, then x3 is the second smallest, and x2 is the largest in R3, and so on. And by considering all possible orderings of the variables, that chunks up space into all of the possible pieces. When you put them together, you get all of space, sort of. We don't get the boundaries between those regions, but those boundaries between them are lower dimensional pieces. And those have Lebesgue measure 0. So that means that the Lebesgue measure of the whole cube, which of course is just t to the n, is going to be the sum of the Lebesgue measures of these disjoint pieces. However, we know that the Lebesgue measure is invariant under orthogonal transformations. So we can just erase this here. And this sum is just going to be the number of permutations, which is n factorial, times the Lebesgue measure of that set, delta n of t, that we're interested in. And so we see that that set, when multiplied by n factorial, has size t to the n, which proves the stated result here. Okay, so this is the actual state space for random vectors of this form. And so the distribution of this random vector is going to be a probability measure on that space. So the question is, how do I compute that distribution? Or equivalently, how do I compute the expected value of an arbitrary function of the vector x1 through xn? And that, it turns out, because the inter-arrival times here are explicit, they're these exponential random variables, this can be computed explicitly as well. And a nice way to describe it is like this. Given any bounded measurable function g on this configuration space delta n, if you want to compute this integral, if you want to compute the expected value of g of x1 through xn, where this is our arrival process, you can do that by integrating the function g over delta n times this density here, lambda n times e to the minus lambda xn, just the last variable, against the n-dimensional Lebesgue measure. That is really just a matter of writing down the appropriate change of variables, which we actually did in a related example in the last lecture, and proving this is left to you on your homework. Now, one quick consequence of this is why the Poisson process is called the Poisson process. The counting process associated to this renewal process, xn, has as its distribution for each time t the Poisson distribution of parameter lambda times t. Okay, let's compute that. Nt is a non-negative integer valued random variable, so all we have to do is compute this probability mass function, the probability that nt equals little n for each non-negative integer little n. And remember, the event that nt equals n is exactly the event that xn is less than or equal to t, but xn plus 1 is strictly greater than t. And so the probability that we're interested in is the probability of this event here, which we can write in this form. It's just the expected value of this function of the random vector x1 through xn plus 1. This function is pretty nice. It only depends on the random vector through its largest two entries. And so using the lemma, we can just compute that this is going to be the integral over delta n plus 1 of, well, I'll note that this indicator can be written as a product of two indicators, the indicator of this times the indicator of that. So that's the indicator that little xn is less than or equal to t times the indicator that t is less than little xn plus 1, lambda to the n plus 1, e to the minus lambda xn plus 1 times n plus 1 dimensional Lebesgue measure. But we have a nice form here. Since the x's are already ordered in here, this first term just means that we're integrating the first n variables over the t-bounded delta set. So that's the integral over delta n of t. And then the final integral that we have to do just means that we integrate from t up to infinity. Now this integral is a simple one for any Math 20b students to finish, and the answer is lambda n e to the minus lambda t. This is just the volume of delta n, which we proved a moment ago is t to the n over n factorial. And so multiplying those out, we get that this is equal to lambda t to the n over n factorial e to the minus lambda t, which is indeed the probability mass function of the Poisson distribution, concluding the proof. So Poisson processes are Poisson distributed at each fixed finite t. But we want to know more than just the distribution at t. We want to know the distribution of nt1, nt2 up to ntk for any finite set of times t1 through tk. That is a slightly more difficult proposition. And in order to do that computation, we're going to discover something on the next slide, which is of independent interest about this process. The result here is that up to symmetry, if you condition on the Poisson process taking value n, then the arrival times x1 through xn have the same distribution as IID uniform random variables on the time interval from 0 up to t. Now, to be clear, when I say up to symmetry, what I'm saying is that the x1 through xn under this condition have the same distribution as the order statistics of IID uniform random variables. That is, I sample n independent copies of a uniform distribution, and then I order those numbers in increasing order. Of course, because that has to be true if it's going to be the distribution of these ones here. Now, a more precise way to say that same thing, and more useful to us, is the statement that I'm making here. If I fix an integer n, and I take n IID uniform random variables on the interval from 0 up to t, then for any symmetric function on that n-dimensional cube, f, the conditional expectation of f of the renewal variables, given that nt is equal to n, is just the expected value of f of those IID uniform random variables. Now, to be clear, symmetric here means that f is invariant under permutations of the indices. F at x1, x2, x3 has the same value as f at x1, x3, x2, has the same value as f at x3, x1, x2, and so on down the line. We're going to prove this the same way we proved the last proposition, using your homework problem. Again, noting that the event that nt equals little n is the same as the event that t is in between xn and xn plus 1. The expected value of f at x1 through xn on the event nt equals n is the same as that expected value on the event that t is in between xn and xn plus 1. So this whole thing here is going to be our function g of x1 through xn plus 1. And that means that we can calculate this expected value by taking this integral over the configuration space of the function f of the first n variables times this function of the last two variables times this density. And then we will do the same thing we did in the last calculation and break this integral up as an iterated integral. We break this indicator up with the xn going with this piece and the xn going with that piece. And we get that the first n variables just integrate out f over the t-bounded configuration space, and the last variable is integrated from t up to infinity. Since f played no role there, this is exactly the same calculation we did last time, so that last variable integrates to lambda to the n e to the minus lambda t. So thus far we've shown that the expected value of f at the renewal variables and the event nt equals n can be computed by this integral here. Now let's use the symmetry of that function f. So that means that this has the same value as f at x sigma 1, x sigma 2, up to x sigma n for each and every permutation sigma n. And so it also has the same value as the average over all of those. Now let's pull that finite sum outside the integral, and that shows us that this expected value can be computed like this. This factor over all out front, the sum over the permutation group of the integral over delta n of t of this permuted function f. Now we're going to do a change of variables for that inside integral in each term in the sum. And that change of variables is just to change x sigma 1 through x sigma n to x1 through xn, which we'll rename u1 through un. That is an orthogonal transformation, and so the Lebesgue measure is preserved. But the reason for doing this is that under this transformation, the domain delta n of t gets transformed to a different configuration space, which I'll call delta n sigma of t, which is the one described by having the variables ordered according to sigma instead of according to 1, 2, up to n. So that means that inside this sum, we just get the integral over delta n sigma of t of f at u1 through un du1 up to dun. Now, just as we noted in our first lemma in this section, the union of all of those permuted configuration spaces is basically equal to the full cube. Now, there are some missing bits, but they are lower dimensional, and so they don't really contribute to this integral. And so this sum here over all of those n factorial pieces that are all disjoint, really up to a set of measures 0 just recovers the integral over the full cube. And so we get that this expected value here is equal to this integral over the full cube times this value here. But we recognize this value here as the probability that nt equals n, as we computed in the last lemma. And so, dividing through both sides by this, we'd get the result that the conditional expectation of this, given this event, is this integral right here, which is, of course, exactly by the change of variables theorem, the expected value of f at independent uniform random variables on the n-dimensional cube. That result is a tool that we will now use to fully describe the finite-dimensional distributions of the Poisson process. In order to state the result, it's actually useful to generalize what the Poisson process is. Remember that we wrote it in this funny way to start. Actually, for any arrival process, nt can just be written like this as a sum of indicators, the sum of the indicator of the interval from 0 up to t of xn. But let's view that as a special case of the following stochastic counting measure. For each Borel set in the real line, we can assign to that Borel set an integer n, which is just this sum here. We sum up the indicator of b of xn. It counts the number of n's for which xn is in b. Now in this language, nt, our Poisson process, is the stochastic counting measure of the interval from 0 up to t. With that language in hand, here is the main theorem which describes the finite-dimensional distributions and beyond of the process nt. If t is a fixed positive real number and b1 through bk is any partition of the interval from 0 up to t by Borel sets, then the stochastic counting variables nb1 through nbk are independent random variables. That is, disjointness of the b's gives independence of the n's. And moreover, if we denote for convenience the Lebesgue measure of a set just as the absolute value of that set, then the distribution of the random variable n of b is a Poisson of rate lambda times the Lebesgue measure of b. So in particular, we can apply this to the case that we were originally interested in, of the process nt itself, by noting that if we have any times t1 through tk that we canonically list in increasing order between 0 and t, then we can take the usual kind of partition of the interval from 0 up to t into those subintervals, and we'll get that these random variables are independent with Poisson distributions. The distribution of the stochastic counting measure of the interval from s up to t is, by this theorem, going to be the Poisson law with rate lambda times t minus s. And notice, by the way, that we can rewrite these things here. Well, this is just nt1. And this one here, because this is a measure, a random measure if you like, but also you can just see from here that this can be written as nt2 minus nt1, and so on down the line. So what we're doing is, just like we did for the random walk, coming up with a formula to describe the distribution of the increments of the process. The increments are independent and Poisson distributed. We're going to prove this now, and we're going to use characteristic function methods. We want to know the joint distribution of this random vector nb1 through nbk that lives in Rk, in fact in n to the k if you like. Now the characteristic function of that is just the dot product of this with a vector that I'll call eta, exponentiated with a factor of I, and then take an expectation. So that is, we need to deal with these kind of functions here, e to the I eta times that random variable. Let's write out what that random variable is explicitly. It's just e to the I eta j times this sum, this infinite sum, the indicator of bj of xl. Now it's going to be tough to deal with these infinite sums, but we actually don't need to, because we're going to condition on the event that the process nt is equal to little n. And remember, that event is the event that xn is less than or equal to t, and xn plus 1 is strictly bigger than t. Well, if xn plus 1 is strictly bigger than t, then that means that the indicator of the set bj of xl, which is less than or equal to the indicator of the set 0 up to t of xl, because bj is a partition piece and therefore a subset of that interval, well, that is 0 for l bigger than n. And so that means that this sum on this event here is really just up to n. And now we can deal with finite sums and finite products, and we'll be able to compute more explicitly. So in other words, the characteristic function of this random vector conditioned on the event that nt equals n can be written just like this, where the sums are up to n. Now a key point here is that this sum here is actually a symmetric function of the xl's, right? Its dependence on xl is just through the sum of this fixed function for each j in the product of x1, x2, up to xl added up. That's a symmetric function. And then I'm taking a product of those symmetric functions. So here I'm taking a symmetric function of the renewal variables x1 through xn and conditioning its expectation on the event that nt equals n. We just proved that that's the same thing as computing the straight up expectation of that same function of IID uniform random variables u1 through un on the interval from 0 up to t. And now we're going to be able to do that computation explicitly. Let's begin by expanding out this exponential of a sum as the product of exponentials. So that's this term right here. We now have a double product. And now combining all of the j terms into one, notice that this product over L, each term in this product is a function of just UL. Now the ULs are all independent, and that means that the expectation of this product over L is the product of the expectations. Now that still looks like it might be tricky inside here. We can't take a further product of expectations because these terms inside here, product over j, are not independent since L is fixed inside there. But we can make the following observation. These are indicator functions. So each one of those terms in that product there, e to the I eta, indicator of b of some variable u. Well, this is just a 0-1 valued random variable. And so this thing takes the value e to the I eta when u is in the partition piece j, and otherwise is just e to the I times 0. Now whatever random value our variable u has, it's in exactly one of those partition pieces. So we can describe exactly that that variable inside here, that product, is just equal to e to the I eta j for the unique j such that u is in bj, and then the exponential is 0 otherwise. And now we can write that in the following convenient way. It's actually a sum. It's the sum over j of e to the I eta j times the indicator that u is in bj. Now that allows us to simplify this expression a lot. This expectation inside here, therefore, is just the expectation of this sum, which is the sum of the expectations. And that's just the probability that u is in bj. But u is a uniform random variable. That probability there is exactly the Lebesgue measure of the interval bj divided by t. And so altogether we get that this inside sum, which we now see doesn't actually depend on L at all, is just the n-fold product of the sum, j going from 1 up to k, e to the I eta j, the Lebesgue measure of bj over t, all to the nth power. Now if we take that 1 over t outside the nth power, what we see is that we've shown that this conditional characteristic function of the random vector n of b1 up to n of bk is this nice simple expression here. So 1 over t to the n times the nth power of that sum. We don't want the conditional characteristic function, though. We want the characteristic function. But that's easy because this is a positive probability event. So all we need to do is say, hey, the full characteristic function, which is the expected value of this, is going to be the sum over all the possible values n of the expected value of this on the event that nt equals n. And we can write that as the sum over n of this conditional expectation times the probability that nt equals n. So let's just write that all out. That's the sum over all n of this conditional expectation we just computed times the probability that this Poisson random variable takes value n, which is right here. The t to the n's cancel, and what we get is an overall factor of e to the minus lambda t times the sum of 1 over n factorial times the nth power of this sum inside. That doesn't necessarily look that simple. However, we can recognize that as the power series expansion of an exponential, a double exponential in fact. This is e to the minus lambda t, the exponential of lambda times the sum, j going from 1 up to k, e to the I eta j, Lebesgue measure of bj. And now let's combine these into a single exponential. In fact, there's a nice factor of lambda there. And better yet, this lambda t here, lambda t is the same as lambda times the sum of the Lebesgue measures of b1 through bk because the b1 through bk form a partition of the interval from 0 up to t. And that means that I can really combine these things nicely. I'll write lambda t as this sum, and each sum in this term I'll combine with the appropriate term over here. And when all is said and done, you can check that this will, factoring an exponential of a sum as a product of exponentials, turn out to equal the sum, j going from 1 up to k, of e to the lambda Lebesgue measure of bj times e to the I a to j minus 1 in the exponential. And now finally, all we have to do is note, as we calculated some time ago, that the characteristic function of a Poisson random variable of rate lambda at variable eta is e to the lambda e to the I eta minus 1. And so we recognize, therefore, that this is the characteristic function of k independent random variables, each of which is a Poisson with this rate. And that is exactly the result that we wanted to show. So we now have a full understanding of the finite-dimensional distributions of the Poisson process. In particular, just like random walks, the Poisson process has independent increments. Now, this doesn't tell us the full story about the Poisson process, although there's enough information here to get the full story, and we'll talk about that a little bit later. But what I want to get to first is the Markov property. Remember that random walks were easily seen to have the Markov property. It turns out that that can be seen as a consequence of the independent increments. And so the Poisson process is going to be another example, this time in continuous time, of a Markov property. We haven't really stated a Markov property in continuous time yet, and so that will be our next goal, the Markov property and Markov processes in discrete and continuous time.